you could take something that is of little value or no value to society and transform it into something that would have high value to society, in fact, could be useful to everyone. My name is Ron Sims, and I'm the head of the Department of Biological Engineering at Utah State University. I want to show you what our students in biological engineering are doing to transform wastes into bioenergy chemicals and other bioproducts in order to improve national security and global sustainability. We do this in a three-step process. First, we produce biomass from waste chemicals. Then we harvest the biomass. Then we use the harvested biomass to transform into bioenergy and other bioproducts. And so I invite you to take a look at what our students in biological engineering are doing to create the future for transforming wastes into bioproducts for society.
I grew up on a farm, so I think farmers were the original biological engineers, and I was always interested in biology and how it's harnessed and used to help benefit people.
My name is Maureen Kesano. I'm a PhD student in the biological engineering department.
When I was learning more about the program here at USU, I realized that biology could be harnessed in other ways to help produce food, but also in the fields of medicine, in environmental cleanup, in energy production as well, and those things really interested me. At USU here, the program was top-notch and great, so it was a perfect fit for me.
I am interested in cleaning wastewater and just water quality in general, because I mean, we all depend on clean water, and so if we clean it up, we are helping not only us, but the environment and the aquatic life in it. And so I think this is a good thing. I'm working on a bioremediation project where we're using algal biofilms to clean up wastewater.
The first part is to grow algae in wastewater to clean the wastewater. And that, in this situation with wastewater, happens naturally almost because there's nutrients in the wastewater and we have sunlight. In certain situations, under certain conditions, algae will grow as a biofilm, so a sticky slime that's attached to a surface. And what I did was learn about materials that the algae will stick to and grow as a biofilm, and I designed a rotating algal biofilm reactor. And that's what these are behind me here.
What I'm doing, I'm trying to optimize the growth of the biofilm so that we can be able to remove as much nutrients, that is phosphorus and nitrogen, from the wastewater, but at the same time produce enough biomass to make other valuable byproducts. I have 2 reactors currently running. Two raceways, one has suspended algae, and the other one has the biofilm growing on the rotating algal bioreactors. And what I'm doing, I'm trying to compare the growth rates and also compare the performance of each bioreactor.
These reactors are submerged in the wastewater partway, and as they rotate, you treat the water, get the nutrients from the water, and then also the algae in the biofilm, when they're up, can take CO2 and also get the sunlight that they need to grow. And the beneficial part of this design is when it comes time to harvest, because it's already a thick biofilm slime, you take the rope that the biofilm is growing on and unthread it, unspool it, scrape off the biofilm. There's your biomass, your algae, and then you can reload the reactor, rewind the rope on, and start again, continue treating the wastewater and growing more algae to be used for energy production while the water is being treated as well.
My research deals with the harvesting side of the biofuel production. We're able to take wastewater and get something useful out of it. Take this product that has no value at all, that has negative value, and we can get something out of it that's worth money. We have a number of issues getting the algae out. It's very small. We're talking scale of millionths of a meter in diameter, these individual cells. It's relatively dilute. The water looks green, but there's not a whole lot of algae in there, relatively speaking. And this algae is negatively charged. So you can imagine, two negative ends of magnets bouncing against each other. They're going to repel each other. What we need to do is get these algae cells to attract to each other, come together, so we can remove them more easily. So in order to do that, we use one method that I'm looking at is this device called a dissolved air flotation unit, also known as a DAF, a DAF unit. It works on a couple of just really simple principles. We have our wastewater flow into two large mixing tanks where we can add in some low amounts of chemicals. That starts this process of bringing the algae cells together so they don't repel each other. After we have 15 or 20 minutes of a mixing time, that pumps into what we call our flotation tank. While the mixing is going on, we have some of this wastewater is pressurized with air. And then when that re-enters the flotation tank, we have lots of bubbles. And those bubbles are able to lift up our algae. By this point, it's already formed larger clumps that we call flocks. Those are then able to raise to the surface and collect on the top. And then we have a scraper that runs on like a conveyor belt system that we're able to just scrape the algae off the top of the flotation tank. So in addition to this, what we call pilot scale DAF unit, which can handle 60 or 65 gallons per minute, I'm also running a small scale, what we call a benchtop unit, which mimics the DAF operation. On that unit, I have 6 1-liter jars where I can vary very easily different chemical dosing, different recycle rates. I can vary different parameters of a DAF and do it all very quickly with different jars. It allows me just to run it quick, clean it out, run it again. I can run that 3 or 4 or 5 times a day, whereas with this large unit, there's a startup, there's a cool down. So I'm trying to optimize it and do a more natural and a more efficient way of getting our algae out of the wastewater.
The algae, when they're growing, they'll take the sunlight and they'll take the carbon from CO2, and under the right conditions, they'll store that in the form of lipids. So what we do is then harvest the algae at the optimal point in time and extract those lipids and use them as a feedstock for a biodiesel product. We take algae, extract the oil from algae, and have this direct drop-in replacement fuel that can then go out onto our existing fuel infrastructure. America has this insatiable appetite for liquid transportation fuels. A long time down, in the future, we might be able to just use electric vehicles on an electric grid or with batteries. But for now, we need liquid fuels. And biodiesel from algae is a very promising solution to that issue.
We use algae biomass to generate biogas, industrial solvents, and bioplastics. So the biogas is basically produced using a series of microbial and anaerobic processes where certain microorganisms break down the algae biomass that can then be used by the methanogens, which actually generate methane gas, to then produce the biogas, which can then be used subsequently to run generators, steam turbine generators, to generate electricity. We can also generate industrial solvents. So we use anaerobic microbes, basically, that can degrade the algae biomass to generate these solvents. And we're doing this currently at a laboratory scale, but the idea is to optimize this degradation of algae biomass to industrial solvents. And once that's achieved, we'll move to pilot scale and then industrial scale to produce these solvents. So in addition, we're also trying to screen different algae that are present in the wastewater treatment facility that produce different types of biopolymers which can be converted into bioplastics. And these bioplastics can replace essentially all the plastics that are used throughout, for example, shampoo bottles, water bottles, etc. You name it, we can replace those plastics with bioplastics, which are naturally degradable and substantially better for the environment.
Well, my research is cyanobacterial biofilms growing in produce water. And produce water is wastewater that's generated from the oil and gas industry. We get our produce water from the Uinta Basin, and currently it's the limiting factor in oil and gas production down there. And we're trying to bioremediate that because the cost of treating that via evaporation ponds can cost up to 80 cents per barrel. And worldwide, there is currently about over 77 billion barrels of produce water produced every year. They are trying to look into growing these cyanobacterial biofilms to bioremediate the produce water, as well as generate many bioproducts like pharmaceutical products and medical industry products. And then after you extract those, you can also use the lipids left over for biofuels generation.
My experience as an undergraduate researcher has really defined my experience here at USU.
Working in a lab as an undergraduate is really important. It's stressed here at Utah State.
I hadn't even taken the orientation for Utah State University, and I was already out here doing research, well, helping with research.
One of the reasons I decided to come to Utah State was because they offered this undergraduate research experience.
I was just amazed that I hadn't even graduated from high school yet, and they were still wanting me to come and work.
I've been able to learn procedures that a lot of other students won't have in my major, which is going to put me ahead of them.
Where usually you don't get involved in research until you're a junior or senior in college, but I wasn't even a freshman yet.
So this has been able to really get me out in the field here at the Logan Lagoons, actually seeing what's going on.
This gave me the opportunity as an undergraduate to experience what research is like, what my major of biological engineering is really like, and I wouldn't have gotten that experience anywhere else.
Biological engineering is working with the city of Logan down here at this wastewater treatment plant, and it's a fantastic opportunity for us. It allows us to take our research out of the laboratory, and the idea with the city is that we solve their nutrient management problems by using the algae growth systems, and then we create these products that can add a stream of revenue for this whole project.
There's enough algae in the lagoons that we can easily power all of the city trucks, all of the garbage, all the recycling, all the just pickup trucks that drive around. We have that ability.
And we'll use the biodiesel generated from the algae to run those trucks.
This project it's applicable not only to the local level, but it's also applicable to the national level.
Wastewater treatment plants like this, there are more than 7,000 in the country. So the type of processes we're doing here can be used in those lagoons as well.
So as a nation, we can really see this as a way to cut back on our fossil fuel usage. That has political ramifications because then we're not buying oil from countries that are unstable. We're making a domestic source of bioenergy that's renewable.
There's wastewater treatment plants all around the world. There's always wastewater that needs to be treated, and growing algae and treating the wastewater with algae is a win-win situation because it's low cost for treating the wastewater, and the energy production on the side can further reduce those costs and help us learn how to scale up the process for algae energy production.
As you have seen, the Biological Engineering Department at Utah State University involves students at every level of their education in working on developing solutions to problems that are important both nationally and globally. Our students graduate with unique skills for transforming waste into bioproducts that make them very valuable to the hiring industry in this area and leaders in the area of transforming waste to bioproducts. The integration of wastewater treatment and bioenergy production represents a game-change strategy for both waste management and sustainable energy development that's being pioneered in the biological engineering department at Utah State University. In addition to the cost savings to both industries, bioproducts from wastes helps to stimulate local and regional economic development through the creation of new engineering jobs, companies, and services. So now you know how our biological engineers design, build, and test new integrated solutions to transform waste into bioproducts. So I invite you to be a biological engineer at USU and be the future.